So a couple more types of trig equations that we'll see and we'll expect it to be able to solve. This is called a multiple angle identity, and the thing that makes it different than anything we've seen before is the fact that we're not just solving cosine of theta equals something, we're solving cosine of twice theta equals something. So there's a couple different ways to approach a problem like this. The way I'm about to show you is the most universal way that works no matter what. So for the moment, just kind of ignore the fact that it's 2 theta. Just, okay, if cosine of 2 theta has to equal something, square root of 2 over 2, well, what does 2 theta have to be? What does twice theta have to be? Well, it could be this, right? If 2 theta is pi over 4, then cosine of 2 theta is square root of 2 over 2. And the only other possibility is, so we're looking for cosine, we're looking around the unit circle there, right? If 2 theta were 7 pi over 4, then cosine of 2 theta would similarly be square root of 2 over 2. So you do that, you essentially just ignore the 2 theta for the minute, and you say, okay, if we're just solving it for 2 theta, then 2 theta has to be either pi over 4, 7 pi over 4, and then don't forget the plus 2 pi n, because that's really what's kind of different in these types of problems. So pi over 4, 7 pi over 4, or any coterminal angle to those two is all that means. So what you do now, and again, this is just a general way that works no matter what, is you divide. So we're just taking this little equation and solving it for theta. So all we should really have to do is divide by 2. But the kicker is that we have to divide absolutely everything by 2. And that includes the 2 pi n. So let me underline the key word there, everything by 2. In other words, to solve for theta, we get, okay, theta equals pi over 4 divided by 2 is pi over 8. To divide a fraction by 2, you just double the denominator. 7 pi over 4 divided by 2 is 7 pi over 8. And then the plus 2 pi n also gets divided by 2, so it's now plus pi n. That's the thing that people have a hard time remembering. So I put this unit circle here because I want to visually look at it. If 2 theta is pi over 4, that means theta is pi over 8, which is right here. You don't see it, but it's right there. So pi over 8 is a solution to this equation. And now we're saying, okay, pi over 8 plus pi n. So pi over 8 plus pi n is over here, or 9 pi over 8. So we're saying, okay, cosine of 2 times 9 pi over 8, which is cosine of 9 pi over 4, should also be square root of 2 over 2, and here's 9 pi over 4, so that's correct. So you don't have to think about that. As long as you just do this step properly and divide this thing by 2 as well, it just works itself out. So 7 pi over 8 is an angle, what, right here? Right, that's 7 pi over 8. So then we're saying, okay, if you go around another pi to what, 15 pi over 8? That's another angle you don't see. That's going to be a solution as well. So multiple angle equations like this, like if this is a 4 or a 6 or a 10 or whatever, are going to have a lot more solutions in the unit circle. This one has 4, it has one here, one here, one here, and one here. But you don't really have to count for that as long as you do this trick here where you divide even the plus 2 pi n by whatever this number is. So let's amp it up a little bit. New example. Solve for theta. 2 sine of 3 theta plus 1 equals 0. So we've seen stuff kind of like this before. The 3 theta is the new thing. But the word we always use whenever we have a trig equation that we need to kind of undo is just to first get it by itself. So all that means is to, okay, 2 sine of 3 theta is negative 1. Sorry, negative 1. Divide by 2, you get sine of 3 theta equals negative a half. So a little bit of algebra to do before we even move on to dealing with the multiple angle. Okay, so go back to the unit circle. If sine of 3 theta is negative 1/2, then you have to look for where 3 theta would have to be. And to me, okay, so we're looking for sine, so I see one, let's see here, right? The sine of 7 pi over 6 is negative 1/2. And if there's a solution there, we're talking about sine, so we can just come across, and we see that there's also a solution there. So the two things that we see 3 theta could be would be either 7 pi over 6 or 11 pi over 6. And then since this is a trig equation, we have to include our plus 2 pi n, which just accounts for all the coterminal angles. Okay? And then the next step is just to divide everything on both sides by 3. And if you do that process correctly, like, you don't really need to worry about what your solutions really look like. It just works out. So 7 pi over 6 divided by 3, that's the same thing as just multiplying the denominator by 3. So we get 7 pi over 18. That's a weird angle. And then we get 11 pi over 18. And then plus, okay, we have to divide 2 pi n by 3. So 2 pi divided by 3 is just like 2 pi over 3. And that's it. So that accounts for all of them. So we've got a solution. So let's see. The 7 pi over 18 is a little less than pi over 2, so it's like up here somewhere. And 11 pi over 18 is like in here somewhere. So we're saying it's hard to see it exactly, but if you're at 7 pi over 18 and you go another like 2 pi over 3 to here-ish, then you're also going to get a solution. And the same thing with 11 pi over 18, which, like I said, is kind of around here somewhere. So you just kind of have to trust the process. This is a lot of solutions within the unit circle. The bigger this number is, the more solutions you're going to get. But it's not like you have to list them all out. You just have to remember to take the 2 pi n and divide it as well. This one is going to involve using one of those identities. And in particular, so this one does involve a sine of 2 theta, but it also involves a sine of theta. So we can't just do it like we did the last time and use a multiple angle identity. So what we're going to do is we're going to use one of the double angle identities. And we have a convenient one for sine of 2 theta. So let me write that down. There it is. That was our double angle identity for sine. Sine of 2 theta equals 2 times sine of theta times cosine of theta. That comes right out of the addition identity for sine. On a test or something, you would be prompted to say, it would say use the double angle identity, blah, 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 to solve this equation. You wouldn't just have to kind of flail around and guess. Okay, so plug that in. So it's 3 times, instead of sine of 2 theta, we're going to say, okay, times 2 sine theta cosine theta, and then that's minus 2 sine theta equals 0. All right, and we still have some work to do, but now we do have something that doesn't have any multiple angles in it. It's just in terms of theta. So let's see, I guess we got to simplify that. That's 6 sine theta cosine theta minus 2 sine theta equals 0. General algebra wisdom here is that if you have an equation and you can just divide both sides of it by some constant, you probably should, because it makes your equation simpler. So notice you can divide both sides of this equation by 2. You don't actually have to, but it does simplify things a bit. So you get 3 sine theta times cosine theta minus sine theta equals 0. Having a 0 on the other side means, okay, we just divided by 0 by 2 and nothing happened anyways. Okay, and now remember the general wisdom here. Do not divide by sine of theta because you'll lose solutions. The move is not to divide, the move is to factor. So never forget about factoring, it never goes away. So the common term we can factor out is sine theta. And what we're left over with when we do that is 3 cosine theta minus 1. All right, and now we have, so the principle of zero products, we have to have either sine of theta equals 0, or we have to have 3 cosine of theta minus 1 equals 0. This part over here is pretty much already taken care of. This part over here is going to require a tiny bit of solving, and I think I can skip a step. Add 1 to both sides and then divide both sides by 3. We get cosine of theta equals 1/3. Okay, so from this part of the equation, you just use the unit circle and you get 2 solutions. If sine of theta equals 0, that means theta has to be any multiple of pi, actually. But as far as what's on the unit circle, that's just 0 and pi. We'll put in the plus 2 pi n at the end. As far as cosine of theta equals 1/3, well, we've seen stuff like that. It's not one of our sort of known trig values, and so we just need to use our calculator, right? Theta is some angle, so what is it? Well, it's just theta equals arc cosine of 1/3. All right, punch that into your calculator, and you get what? You get 1.23. And then think back to when we did equations like this. Okay, if 1.23 is a solution for this, then because it's cosine, actually so is negative 1.23. Negative 1.23 is the angle in the fourth quadrant that must also have that the cosine of negative 1.23 is 1/3. Look on a unit circle to know what I'm talking about. It's easier to tell if you're just looking at it. Okay, so those are our 4 angles on the unit circle that satisfy this. Finally, just put it all in one place. It doesn't matter if you put them in order. It's 0, pi, 1.23, comma, negative 1.23, and then plus 2 pi n. So those, or any angle that is coterminal to those 4, are a solution to this equation. Okay, so that's a lot of stuff. These are not easy at all, so we kind of had to do a little bit of almost everything just to solve that problem. All right, I want to do one more example of this kind. We have seen this type of thing before, but these problems are tricky and do kind of require us to throw everything we have at them. So we have negative 2 sine squared theta minus 3 cosine theta plus 3 equals 0. So this almost looks like a quadratic type of equation, except the problem is we have sines mixed in with cosines. So once again, we're going to bust out our faithful identity. We're just going to use the classic sine squared plus cosine squared equals 1, except we're going to rewrite it as sine squared theta equals 1 minus cosine squared theta. So we're going to replace that first sine squared with 1 minus cosine squared, and that way we'll have an equation that's entirely in terms of cosine, not both. So we got negative 2 times 1 minus cosine squared theta minus 3 cosine theta plus 3 equals 0. And now we got to clean that up. So distribute that negative 2 plus 2 cosine squared theta minus 3 cosine theta plus 3 equals 0. Combine any possible like terms, so that negative 2 will go with that 3. 2 cosine squared theta minus 3 cosine theta plus 1 equals 0. And now we have what we had called an equation of quadratic type. So it's still a trig equation, but it has the form of a classic factorable quadratic equation. So you can factor it right from here if you want to be bold. For the rest of us, the move is to make a substitution. So let's use x. Let's let x equal cosine of theta. Because now this whole thing becomes literally just a classic quadratic that we have to factor. So we have 2x squared minus 3x plus 1 equals 0. We're still going to have to go back in the end and deal with theta, and that's fine. So again, whatever your factoring technique is, mine is just kind of to do this. Okay, I know it has to be a 2x and an x. All right, because that's the only way to get 2x squared. And now let's see, I know I need a plus 1 on the end, but I need a minus 3 in the middle. So the only way to get that plus 1 is going to be with a minus, and let's just see, the only factor is a 1, or 1 and 1. So we have 2x squared minus 2x minus x plus 1. Boom, there it is. That's the factorization. So don't jump to using the quadratic formula or something until you've at least tried to factor it. So we have 2x minus 1 equals 0, or we have x minus 1 equals 0, which means, I'm going to do a little quick algebra here, that means either x equals 1/2 or x equals 1. And now we have to remember that we did do a substitution. We're not solving for x, so we're not done. We plug a theta back in, right? We know that x equals cosine of theta. So now finally we have cosine of theta equals 1/2 or cosine of theta equals 1, and it's unit circle time. So from the unit circle, for cosine of theta to be 1/2, it looks like an angle of pi over 3 will do it. And then there must also be 1 in the fourth quadrant. It looks like an angle of 5 pi over 3 will do it. And for cosine of theta to be 1, go away. For cosine of theta to be 1, theta would have to, well, actually the only possible angle on a unit circle with a cosine of 1 is 0. Okay, and then, if you're confident, it's not like you have to go back and check those answers. Just be concise. Theta is equal, I'm just going to put them in order. You don't have to. 0, pi over 3, or 5 pi over 3, plus 2 pi n, right? Those three angles, or any angle coterminal to any of